Good afternoon, my name is Omar Sosa. I'm going to be talking to you about the incubator design, the phase B. The subsystem that I am in charge of is the mechanical subsystem. First, we have the outlines, just like with every other standard project. First, we have the subsystem trait studies, the architecture into components, the trait studies for the three critical components, the subsystem risk assessment, and finally the complete project planning. First, we have the subsystem trait studies, the first option for the mechanical subsystem. We have a prototype pod portable incubator. We have a sketch that was made for this design. As you can see, the mechanical components of this design include the bed chassis, the wheel frame, the wheels, and the collapsible clear casing surrounding the infant. As you can see, I have my references here, which are the portability, the investment cost, the quantity of major components, and its weight. For the second option, we went with the conventional incubator, which is a semi-portable incubator. Same with the other one, we have here 5 major components. Same as with the other, the bed chassis, the wheels frame, the wheels, the clear casing, but in this one we have the door hinge. The last one did not have the door hinge because it's a collapsible clear casing and does not need a door hinge. Same as with the others, my references are the same. Portability, this one is semi-portable while the other is fully portable. The investment cost, it's a little higher than the other one. This one has 5 major components while the other one has 4. And the weight, it's much more heavy than the last one. It's 120 kilograms. And so our option 3, which is the option that we're gonna be basically taking into account, it's a new prototype also drawn of a new incubator. That is basically what we're going to do over the next phases. And just as with the other one, I have to design the mechanical components, which include the wheels, the incubator chassis, the screws for the frame, the chassis, and the casing, the door hinge, the clear casing, and the wheel frame should be collapsible and removable, both. Same as with the other one, the references are the portability, the investment cost. This one should be fully transportable. The investment cost is $500 US, which is a bit lower than the other ones. The quantity of major components is 6, and the weight, it's expected to be 10 kilograms. And so now for my 3 critical components, first I'm going to be showing you the 3 options that we just saw. As you can see, my criteria was cost, which is very important, weight, also important for portability again, the complexity in building it, and the quantity of major components. If you see by the total of the 3 sums, the option 3 seems like the best option, which is also the one that we're going to be developing. And so here you have my subsystem architecture and the hierarchy diagram. As you can see, my subsystem is mechanical, as I said before, and what I'm basically going to be covering is the transport wheels and the frame, which includes everything that goes under the incubator, designing wheels and a frame that can sustain different add-ons for the incubator, including oxygen tanks, every other piece of hardware that you may need to help the patient. And so the incubator chassis, we're trying to do it with a new material, hoping we can, do something new. If not, well, we have 2 or 3 other options for this one. And for the casing, we are going to probably be using some sort of polymer or some sort of acrylic material for this. Obviously, this is just a preliminary diagram. During phase C1, we'll be seeing, more development on this. And so here you have my subsystem architecture into components. As you can see, I have 5 components that I'm gonna have to be designing. As you can see, the chassis or the body, the wheels, the wheel chassis, the door hinge, and the clear casing, which is what's going to be covering the baby from the environment, obviously. And you can see how they all, connect in this diagram. Okay, so my problem statement for the mechanical component of my subsystem basically includes that a typical baby approximately weighs 120 pounds and is approximately 3 feet in height, 3 feet in length, and 2 feet wide. Sorry, not the baby, the incubator. The approximate infant weighs 7 pounds. So what we want to do is we want to reduce the incubator size, its weight, and improve its portability. To accomplish this, we need to select new materials for these components as well as a redesign based on an already existing model. To accomplish this, we have to calculate and find possible materials that can, comply with these parameters, which state as such. Heat resistant up to 350 Celsius. Basically, the chassis should be heat resistant up to that temperature. The whole system should be resistant to humidity and fungus. We also have to calculate the stresses and strains, taking into account the weight of the baby and other components. The metal components should be resistant to corrosion, that's very important. And finally, the whole thing should be a material that is high resistant, light, but built for transport and for a lot of movement. That is very important for us. And so now I'm going to show you my 3 critical components for the mechanical incubator, for the mechanical subsystem, sorry. And so the first one we have is the material for the incubator chassis, for the body of the incubator. My 2 options are plastic or fiberglass, and my criteria for evaluating them was basically the cost, the durability, the weight, and the heat resistance, which obviously they're all very important, especially durability, weight, and heat resistance. And as you can see from the table, it would look like fiberglass has won as the material. It's still not the final answer, but we're inclining toward that material. And so for the clear casing, we have 2. We have plexiglass and we have glass. Plexiglass is what is used right now, currently on the market. So it's highly likely that we go with that one. But again, the same criteria that we use to evaluate are the cost per square foot, the durability, the weight, which is very important for supporting, and the heat resistant. Again, those are all very important. And if you can see on this table, the material that won was actually glass, surprisingly enough. However, we don't see actually glass in today on any incubator. We basically see plexiglass or some sort of other acrylic material. And my 3rd critical component is the material for the wheel frame. Very important because it's what's going to be sustaining the chassis, the baby, and every component on the incubator. My criteria was pretty similar as the others. The cost, very important. Corrosion resistance, maintenance, and durability. And so I added corrosion resistance because my 2 options for material were iron and steel. I didn't specify which iron or steel yet. I'm still debating it since there are so many, obviously. But the kind of clear choice seems to be iron, comparing its maintenance, its durability, and its cost. Well, the costs are, a little bit the same, but still. And so my risk assessments, there might not be that many risks containing the mechanical part of the incubator. However, I did find such risks, which include failure of the wheel chassis, such as the mechanism, the wheels not properly secured or installed. Basically, mistakes that could happen when assembling the incubator that has to be made from that it has to be done by someone who understands what they're doing. Other possible risks include poor maintenance, of the wheels or any other part of the incubator. It can cause any sort of problem, even though it's minimum. If something were to happen, the consequences would be really, really, really great, really, really, really high. And so here you have my risk diagram. As you can see, I just explained my risks, and you can see them here. And this is my project plan for phase C1. I hope to be done by June 7th, hopefully, if everything goes up to schedule. And that's basically it for my presentation. Thank you for your attention.